Look at a dense 3 by 3 grid of variables. Without a structured method, extracting a single solution from this array is practically impossible. But every square array of data carries a single hidden governing number. In mathematics, we call this the determinant. The determinant forces all square matrices down one of two distinct mathematical paths. If the determinant equals exactly 0, the matrix is locked. We call this a singular matrix, meaning the system cannot be resolved. If the determinant is any non-zero value, the matrix is non-singular. This provides the mathematical pathway required to invert the matrix entirely. Testing this core scalar is the strict prerequisite to dismantling complex grids of variables. Evaluating the determinant of a large matrix requires breaking it down into smaller 2 by 2 blocks. The calculation starts with straightforward cross-multiplication. We multiply the top left element by the bottom right and subtract the product of the remaining diagonal. Scaling this up to a 3 by 3 matrix means we expand the grid along a single row or column. We begin by selecting a starting element, like the one in the top left corner. Isolating this value eliminates its entire intersecting row and column from the calculation. The 4 remaining untouched elements snap together. This forms our foundational 2 by 2 block. We repeat this extraction for the next elements in our chosen row, alternating our operations between addition and subtraction as we move across the grid. By repeating this process, higher-order matrix operations are systematically reduced to basic cross-multiplication. This mathematical operation also governs physical 2-dimensional space. Take any geometric triangle plotted on a coordinate plane, defined by 3 physical points. We map the x and y coordinates for these 3 points directly into the first 2 columns of a determinant matrix. Because a determinant requires a square matrix, we fill the empty space with a column of 1s. Running the standard determinant expansion on this new grid and multiplying the final result by 1/2 gives us the exact physical area of the triangle. The determinant utilizes the exact same structural logic to process abstract algebraic variables and literal geometric polygons. Returning to our matrix algebra, the manual strike-through process we used earlier needs to be formalized into distinct trackable units. Let's look at the subdeterminant left over after deleting a specific row and column. This raw extracted submatrix is called a minor. By itself, a minor has no spatial awareness. To make it useful, we have to calibrate it based on its original coordinates in the larger grid. We use a positional formula, -1 to the power of row plus column, to generate an alternating grid of positive and negative signs. Applying this corresponding sign to our minor transforms it into a new functional unit, the cofactor. A cofactor is a localized block of data, mathematically anchored to its precise location within the global matrix structure. The next step is to systematically generate a distinct cofactor for every single element in the original matrix. This creates an entirely new 3 by 3 grid built completely out of calculated cofactors. To prepare this grid for solving equations, it must undergo a final spatial transformation. We perform a transpose operation, converting the rows into columns across a diagonal axis. This final transpose structure is the adjoint matrix. The adjoint pipeline systematically scales local sub-elements up into a unified matrix, readying the data for full inversion. We calculate the adjoint for one specific reason: to find the inverse of the original matrix. The mathematical formula for the inverse takes the adjoint matrix and divides it by the original determinant. Notice the specific placement of the determinant as the denominator in this fraction. If the determinant is 0, the fraction forces a division by 0. The math breaks down immediately, and the matrix is declared singular. Because it dictates whether this fraction can exist, the determinant acts as the definitive gatekeeper, deciding if a matrix can be inverted. We apply this entire inverse pipeline to solve complex, multivariable systems of linear equations. We take a dense system of equations and format it rigidly. We pull out the coefficients to form matrix A, stack the variables into a column matrix X, and isolate the constants into matrix B. This condenses the entire system into a clean algebraic expression. Matrix A times matrix X equals matrix B. To solve for our unknown variables, we isolate matrix X by multiplying both sides of the equation by the inverse matrix of A. Substituting the inverse symbol reveals the complete computational pipeline we just built. We start with raw isolated elements, extract their minors, assign positional signs to create cofactors, transpose those into an adjoint, and scale by the original determinant. By anchoring the entire calculation, the determinant turns an unsolvable block of data into a precise mathematical solution.